Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in Chapter 7, part of this playlist that I'm calling Classification Analysis. And let's jump to today's topic, which is Quadratic Classification Functions. So the setting is, assume we have n observations with p variables per observation, so they're vectors, that have been previously classified into k groups, G1 through Gk. And we wish to classify one observation vector y with the p variables, an unknown sign group, into one of these k known groups, G1 through G2. And this quadratic classification method is used like this. First, we assume we are not assuming any distributional properties. Now, unlike linear classification, where we assume there's a common covariance matrix with each group, the quadratic classification does not assume equal variances. And it's just a slight modification to the linear classification functions can be made, and it creates these quadratic classifications. So to classify an observation vector y, we compute the distance from y to each group mean vector yi bar. And we do this for I equals 1 to k. So we have k distances, and the distances are the statistical difference. It's actually the squared statistical difference, di squared, and it's a Mahalanobis distance. And so the difference between linear classification and quadratic classification is this matrix here. In linear classification, we assume all the covariances are equal, and we use a pooled covariance matrix, and then we're able to get rid of the quadratic term when we simplify it. But here, since we're using the sample covariance matrices for each group, you can't make that same modification, so it stays quadratic. And we just want the smallest distance, and whatever the smallest distance is, that's where we assign that new y vector. Now, one note, according to Wikipedia, quadratic classification functions are the most commonly used method for obtaining a classifier. Now, here's quadratic classification with the normality assumption. And one of the reasons I'm covering this is the built-in function in R, QDA, assumes normality. Okay, but you don't have to, but it does, so I'm covering it. And so if we assume normality with unequal covariance matrices, and that says the data, for each group is multivariate normal with some mean vector and covariance matrix, then the classification rule becomes this: assign y to the group for which qi is maximum. And so we calculate qi for each group, given this y. And if you look, let's see if I can get them both in. Oh, I can. So here is the statistical distance, when no normality is assumed. And that's this piece right here. So what we do is we have this extra constant, and that deals with when you have the ratio of multivariate normal densities, or not the ratio, but a multivariate normal density. Then you get this determinant of the covariance matrix. And then we take it times a minus 1/2. So we want di squared to be the smallest distance, and then we want to maximize this quadratic rule. And this is the qi is what the built-in function in R uses. And we'll derive both from scratch and then show that the one is equal to the QDA function in R. Now, in this example, we got the data from an FTP site, and it's called T617 fish data. And this is actually the same example that we used in linear classifications, so that way we can compare to see which method does better, linear or quadratic. This is Bait and Tack and Bader in 1958 compared judges' scores on fish prepared by 3 different methods. 12 fish were cooked by each method, and several judges tasted fish samples and rated each on 4 variables. Now, each entry is an average score for the judges on that fish. The 4 variables are aroma, flavor, texture, and moisture. So let's fire up R here. We read the data in. Now, there's no header, which means it doesn't have variable names, so we I give them variable names, and then I print out the first 6 observations. This is it. And so method tells us which method 1, 2, or 3 is used. I want to calculate the sample size for each method, and there's 12 in each, and that's stored in N. Now, we're not going to go over these. A lot of these functions were covered in previous videos. And so to calculate the mean vector by group, we use this function, and it comes out this way. Now now we calculate the covariance matrix for each group, and we use this by function, which is very powerful in R. And so this is the covariance matrix for method 1, and it creates a list. So SI is a list. There's the covariance matrix for method 2, method 3. Now let's use the quadratic classification rule or function that doesn't assume normality. So if our next y is this vector 5, 4, 6, 5, we want to assign it to which method we think the fish was cooked with. This is the function. So the workhorse is this Mahalanobis distance. We're taking it, taking the next y and using and comparing it against each mean vector in this MV mean vector by group, and we're also using the covariance matrix for each sample. And so we get this. And notice that the method 3 has the smallest statistical distance from our next observation, so we're going to classify it as group 3. Now, if we use 5, 6, 6, 5 as our next y and run it through the same function, notice that method 1 has the smallest statistical distance. So the distance between this new observation and the group mean vector is smallest for group 1, so we assign it to group 1. Now, what I want to do is use this non-parametric quadratic linear function on y itself to see how well it classifies itself. And we know the group for each observation, but let's just see how this method would classify itself. And so we do that. And then so for each observation, we calculate the statistical distance between that observation and the 3 group mean vectors. And so temp is going to be a 3 by 36 matrix, and the rows represent the statistical distances from that observations to those mean vectors. And then we want to know which one of those is minimum, and then so it'll give us a 1, 2, or 3, and then it's stored in predict fish. Now let's look at a table of actual methods cooked by the fish and the predicted method of cooking the fish. And here it is. So the actual fish 1, we predicted a 1 11 times, and we predicted a 2 1 time. When the actual fish was 2, we misclassified it as a 1 4 times, and correctly 7, and 1 wrong, we classified it as group 3. And then it was a 3, we misclassified 1 as method 2, and then 11 as correct. Now, one note that there's 5, 6, 7 misclassified here. In the linear classification, there were 9 misclassified. So we actually did better using quadratic classification than we did linear classification. Now let's use the built-in function, and this is pretty much what everybody uses. So the QDA is the built-in function, and we want method by these 4 variables. Boom, it stores the model and fit. And now we want to predict fit, so that means it uses itself to predict what fish or method of cooking would be used. So we just want the class, and so QDA fish, that's the predictions. So let's look at the actual fish, a table of actual cooking method of each fish by the predicted using this QDA function. Remember, it assumes normality, and this is it. So they're a little bit different. There's still just 2, 4, 6, 7 misclassifications. So it does better than the linear classification rule, but it's a little bit different. Instead of 4 and 1, it's 2 and 2. So, but now to me it's like, well, okay, I got to understand that. What's going on? So let's try to rederive this QDA method by scratch. And so we create a new function. And this is actually the same function. I stored the results to temp up above, but we called it temp2 here. And it has this extra piece, the minus log determinant of the covariance matrix for each group. And then of course we divide each of those by 2. And then it creates a 3 by 36 matrix, but then we want to know which one of these is maximum, right? This quadratic classification function, we want the max. So we store it in predict fish 2. And let's look at the actual fish method of being cooked by the predicted. And this is it. So 10, 2, 2, 2, 8. And this is actually the same pattern as the QDA function. But let's table this new predicted fish 2 against the QDA, and notice that it's a perfect match. That the predicted fish 2, the derived from scratch, assuming normality quadratic classification function versus the built-in function QDA. They're perfectly aligned, as they should be. And then if we look at where they differ, so we use the predicted fish, which is the non-parametric quadratic classification, versus the parametric, assuming normality predicted method. And this is it. And so the misclassification, there's 3 when there's a 3 here. So it's method 1 was predicted by the non-parametric, method 2 is predicted by the normality, and there's a 1 here. The rest were okay. Okay, so I'm at 12 minutes, so I got to stop. Hope you enjoyed this. I sure did. Please like it and subscribe so you don't miss the next one. Now the next video will be on nearest neighbor classification. So see you then.